Hello everyone, and welcome to lecture number 7. Today we're going to be finishing up with TCP by talking about congestion control, which is a pretty big topic unto itself. In the last lecture we talked about TCP, and this was building off the previous lecture on reliable transport. We saw that in TCP we use cumulative acknowledgements. This, unlike the simpler protocols we saw earlier, any data segment can carry an acknowledgement as part of its headers. Receivers buffer out of order segments for later reassembly, so that was a feature of the selective repeat protocol that we talked about in the lecture before. And in that lecture we talked about ways of setting appropriate timeouts. So when you are expecting an acknowledgement, you have to eventually at some point give up waiting for an acknowledgement because you imagine that the packet was lost. To set the acknowledgement timeout in TCP, we use an exponentially weighted moving average of recent round-trip times and also recent jitter. Jitter is the variation in round-trip time that we experience, like the variability in round-trip time. And then those two things together can let us set a reasonable threshold after which, if we don't receive a response, we can be pretty confident that the packet was lost. The number of in-flight packets is determined by what we call a window size. And this window size determines the throughput of the connection, in other words, the quantity of bytes per second that you're transferring. And TCP has two different ways to control its window or throughput. So the first one is called flow control. And this allows the receiver to tell the sender how much space it has left so the receiver's buffer does not run out of space. So this is to prevent overwhelming the receiver with too much data. It's called flow control. It's a pretty simple implementation. Now today we're going to be talking about the other thing that can be overwhelmed, which is the network. You don't want to send so much data that the network can't handle it and the network drops packets. But unlike flow control, you have no direct observation of what the network status is. You can't ask the network what its capacity is. Instead, you have to kind of experimentally figure this out, and the network conditions can change over time, which makes it even more challenging. And of course, every connection you make is going to go through a different path in the network. So therefore, you never really can predict ahead of time what the appropriate rate is to send data. So TCP has a set of sophisticated ways to figure out how much throughput the network can handle on a given connection between two hosts, and that system is called congestion control. Okay. We also mentioned last time that in TCP there's a three-way handshake needed at the beginning to exchange random initial sequence numbers. We also mentioned that closing a connection involves a kind of handshake involving these messages called FIN messages. Okay, well, let's get into congestion control now. So congestion is a situation where you have a network that's overloaded, and when that happens, the links are sending data as quickly as they can, so routers have to queue up data that's waiting to be transmitted. When the router queues become full, packets are dropped. There also can be this is observed by the sender not getting an acknowledgement to some packet that they send. It's important to realize that drop packets are something you want to avoid. Drop packets lead to inefficiency, not just delays. Okay, and drop packets can compound a network congestion problem that you have. So if the network is congested, then queues will be full, so packets will be lost if you try to transmit them. When you lose a packet, you end up retransmitting it, but that retransmission might add additional load to the network, and that can cause more congestion and more loss. So if you just blindly try to send packets as quickly as possible, and you send them at a rate that's much greater than the network can handle, most of those packets will not get to the final destination. They'll be dropped, but while they are traveling to the final destination, they're consuming precious resources and blocking other traffic from flowing. So sending data too quickly is leads to a self-destructive feedback cycle where you're causing more retransmissions are causing more congestion that are causing more need for retransmissions, and overall fewer of the packets in the network are actually reaching their destination, and a large fraction are just wasting space because they're going to be dropped at some hop before they finally reach the destination. So it's better to wait if you think it's likely that a packet is going to be dropped before it reaches its destination. And by doing that, you're giving the network time to empty its queues and send the data that's waiting, so that more data can fit in the queues and eventually be transmitted. Like I said earlier on, we don't have direct observations or information about what's happening in the middle of the network. We only have end-to-end observations of network performance. So when you receive data from your the host that you're talking to, the host can put information in the headers of the packets it's sending, but the routers don't generally change headers to provide any information to the end hosts. Okay, so it's a challenging problem to solve for that reason. Now, if we think about what would happen if we did not have congestion control, I kind of described it, but let's just see a little simple illustration. And this illustration involves just two computers in a very simple network where there's just one router in between them, and there are two links. And the laptop in this diagram has a fast link, a high bitrate link. So what it might do is send data as quickly as that link will handle. But the problem is that the second hop, the second link in this path, is a low bitrate link, so the router won't be able to send out data at a rate sufficient to consume the data that's coming in. Okay, so packets will be queued up in this router, and eventually they'll be dropped. A large fraction of them will be dropped. The fraction that is dropped will be whatever you get when you subtract the high bit rate from the low bit rate. That's the quantity of data that will be dropped, right? So you'll end up just having periodic packets being delivered and a lot of in-between packets being dropped. The acknowledgements will come back, of course, at the slow rate, whatever rate they're being received. And your receive buffer will have a lot of gaps. You'll have a lot of missing segments because a lot of intermediate data was dropped. So you'd need large buffers. And there would have to be a lot of retransmissions. It's basically the problem here. The problem becomes, I think, a little more obvious even when we look at a network where there are multiple routers and multiple users. So in this situation, I have a network where imagine every link has equal capacity and that maximum capacity is 10. Let's just say 10 bytes per second, 10 packets per second, whatever the units you want to think about. And both A and B are sending at that maximum rate for the links that they have at the start. At some point, they're both trying to communicate to destination D in the lower right. So they both have to travel through one link, and that one link is a bottleneck, right? Because in total, A and B are trying to send 20 packets per second, let's say, to D, but the link can only handle 10. So some packets have to be dropped in the steady state in this router that is right before that bottleneck link. Let's just say somehow that the router figures out a fair way of doing this so that each of the two connections gets half of the resource. So they each get 5 packets to go through and they each drop 5 packets. Now, the inefficiency comes into play when we consider what's happening in these links leading up to the bottleneck. If we're dropping the packets kind of like 2/3 of the way or half the way to their destination, but in the earlier parts of the path, we're wasting capacity that could have been used earlier. So if we had just dropped those packets earlier, then for example, E would be able to communicate with C. Right now, if E wants to communicate with C, there's no capacity left on that path for it to communicate because B is using that capacity, and it's wasted capacity because half of those packets are going to be dropped anyway by the next router, right? So it would be much better if A and B could somehow figure out that they should only be sending at a rate of 5, avoid these packet drops, and that would avoid inefficiency, and therefore this link between this diagonal link in the middle here would only have a throughput of 5 from B, and E would be able to use the remaining capacity to talk to C, right? Okay. Now, in general, in networks, there are two kinds of congestion control. TCP uses end-to-end congestion control, which is to say that the routers in the core of the network don't give any feedback about what's happening. And therefore, congestion is inferred from observed packet loss. Or later on, we'll see that you might be able to look at round-trip time to infer congestion. That's a little more sophisticated. But anyway, the end-to-end behavior, in short, between hosts is what you use to infer congestion and control your connection. Now, there is an alternative, theoretically, which is network-assisted congestion control. This is where the routers actually add some information in the packets they're sending that tell the receiver a little bit about what it should do to control its connection to prevent the routers from becoming overly congested and dropping packets. And TCP, IP, or is it TCP? I forget. There's a header in either TCP or IP called the Explicit Congestion Notification, or ECN header, that does allow the routers to signal congestion, and theoretically they can indicate what bit rate they want the end host to use. However, in practice, this is not used much on the public internet, at least, because on the public internet you have a lot of routers that are not necessarily cooperating with each other, and hosts don't really know what to expect from the routers. So this is not done on the public internet very much, although on private networks, like between data centers and in big cloud providers, and in cellular networks, this kind of thing can be done and is sometimes done. Okay, but in this lecture, we're going to be talking mostly about the classic end-to-end style of congestion control that TCP does. Okay, where the routers don't really participate, and they're just, they just drop packets when they have to, but they don't give any information about whether they're close to dropping packets or whether they are dropping packets. Okay. So to observe congestion, we, as I said before, the way we figure that out is by seeing whether packets are dropped. We don't expect the receiver to be dropping packets, because we already have this flow control mechanism built into TCP that tells the sender how much data it should be able to safely send from the receiver's perspective. So if a packet is lost, we know that loss is not we expect the loss is not happening at the receiver's side. So instead, if a packet is dropped, then it's probably due to the network. But in general, we don't necessarily know that a packet is dropped. All we know is that we didn't get an acknowledgement before a timer expired. And there are two possibilities here. Either our timer interval is too short, in other words, the timer was wrong, so we thought it might be a loss, but it actually wasn't because the acknowledgement came later. If that happens, that's kind of an error in our judgment of the round trip time. But the exponentially weighted moving average that we talked about yesterday for computing the timer will adjust itself, will take that data into account and cause the timer next time to be higher. So that should correct itself, assuming that the network is relatively consistent in terms of round trip time. If the network is totally inconsistent in its round trip time, then all these protocols kind of fail in some sense. But that shouldn't happen. So in fact, when packets are dropped, we can pretty safely conclude that the network was congested, and it's the routers that are dropping the packets because their queues are full. Okay. So with TCP congestion control, what's happening is that the sender is trying to estimate an appropriate congestion window, which is to say the number of packets that can be sent during a round trip time without overwhelming the network, the links and the routers in the core of the network between you and the receiver. You keep track of the number of in-flight packets, actually what you're tracking is the number of bytes of data, not packet numbers. But anyway, that data that's in flight has to be smaller than both the congestion window that you're estimating and also the receive window, which is that flow control window we mentioned last time. Okay, so you don't want to overwhelm the network. That's the first component of the minimum. And you don't want to overwhelm the receiver. That's the second component. And if you somehow determine that a larger congestion window can be used, what you're saying is that you're going to send at greater throughput, And by doing that, you're going to put greater load on the network. But you might go too far. If you do go too far, then you'll see packet loss because you're sending too fast, you're overloading the network. And when you do observe packet loss, what you do in reaction is to decrease the congestion window. So somehow your TCP congestion control algorithm has to like set this congestion window, estimate it, and raise it and lower it appropriately to adjust to dynamic changes in the network. And if it's too high, that you'll observe packet loss, and that means you should probably lower the congestion window to slow down. But if you become slower, eventually at some point you should try to get faster, because there's always a chance that you overslowed and the network can actually handle more capacity. There's also the chance the network got faster, and you want to test that. So there's this constant kind of like probing up by increasing the congestion window, like going faster, until at some point you notice that you've gone too fast and you have to slow down. That's basically in a nutshell what TCP congestion control does. And you should have noticed that the key challenge here is for the sender to choose its congestion window size appropriately, so the network is not overwhelmed, but also so that you're not being too conservative, you're not going too slow and unnecessarily slowing your connection. Okay. So TCP Reno is the name for a particular TCP algorithm that was very popular in the 90s and the early 2000s, and is still in use to some extent now. If you do a Wireshark trace for the Wireshark lab and look at the TCP behavior on your machine, you probably will not see TCP Reno behavior, because actually nowadays there are some different, more sophisticated algorithms that are used. I'll mention those at the end of this lecture. But we're going to spend a lot of time today talking about TCP Reno because it was popular for a long time. It was successful. The book talks extensively about it. It solved a lot of problems in the early internet and allowed the internet to scale by solving those congestion problems. Because before congestion control in, I think, 1988, there was a so-called congestion collapse on the internet where too much traffic caused the whole network to be congested and poor performance for everyone. All right, but like I said before, we're going to see a lot of these graphs, these plots, where on the y-axis we have the congestion window size, which is the throughput or the speed of the connection. And on the x-axis we have time. And this represents, so we'll see basically how quickly the sender is sending its data on this line plot. And we'll see what adjustments are made to the send rate, which is to say the congestion window size, over time. And at some point at the top of this plot is always going to be some point which is the maximum speed that the network can handle, which is the Q saturation point in this diagram. So if you try to send data faster than a certain point, queues will start to fill up and packets will start to be lost. Once those packet losses will be observed by the sender, and the sender should reduce its sending rate. And then it should start increasing it again to try to reach the maximum again. So what TCP Reno does, I'll talk in more detail in the next couple slides, but basically you start off not knowing at all how fast the connection is going to be. So you start with a really slow connection. Then you have a phase where you double your speed every round trip. You double your window size every round trip because you want to quickly discover what the maximum is of the network. And a good way of doing that is to grow exponentially, right? Double your speed every round trip. If you keep doubling, you can get to a very large number very quickly, right? Exponentials grow very fast. So eventually you will reach the maximum, and that means you will start losing packets. At that point, you have important information. You have a pretty good estimate of roughly what the maximum speed of the network, what rate you can send at without losing packets. So in this case, it went up to like 145 or so was the window size at which packets started to get lost. I'm not sure what the units are. This could be like kilobytes or megabytes or something for the window size. At that point, you want to reduce the speed you don't want to go down too slow. You don't want to go back to the beginning because you do have some information. You know that it's roughly this high. So what TCP Reno does is it cuts the sending rate in half. This is called the multiplicative decrease of Reno. And then at that point, you know that you're sending at a rate that's roughly it's somewhere around half the maximum rate. You don't know exactly how close it is to the maximum, but somewhere around half. And because the point is that when you doubled, you actually jumped quite a bit from the previous round to this next round. So that doubling could have gone way over or just a little bit over. You don't know. At that point, after you get a packet loss, you half the rate, and then you increase linearly. So every round trip, you increase the size of the window by a constant, which is actually one full maximum packet size, which is like usually 1.5 kilobytes. Until eventually you reach the maximum again in this simple example where everything is static, and then you have it again, and so on, right? So that this design keeps you close to the maximum transmit rate, and it lets you discover that maximum pretty quickly. But you're always kind of like adjusting up and adjusting down in reaction to packet losses, and in reaction to, if everything's going well, you always just try to bump it a little faster to see how much faster you can go, basically. Okay. So to put that into rules that are a little bit more concrete, we can say that TCP Reno has 3 phases. The first one is called slow start, because initially we have no idea what the capacity of the network is. So we start with the window size being equal to 1 packet. The MSS is the maximum segment size. Usually it's around 1.5 kilobytes. So you send 1 packet. When it gets back, every round trip time, in other words, when you get an acknowledgement back, you double the congestion window. So you send twice as much next time. Okay, so at first this will be like pretty slow, but at first you really have no idea how fast it is. It could be that the connection really is pretty slow. So it doesn't, even though you're starting at 0, because you're doubling every time, you can get to a large number pretty quickly. But eventually you get a packet loss by observing a timeout. Like, in other words, you don't get an acknowledgement in the time that you expect to, within the time that you expect to. That means that after all this doubling, you've started sending at so high a rate that the network is overwhelmed. So at that point, you cut your congestion window in half, and you move to the next stage, which is called congestion avoidance. In this mode, you're no longer growing exponentially, but you're growing linearly. So every time you get an acknowledgement, you increase the congestion window by 1 packet size. And but at some point you will get a packet loss. If there's a packet loss, there are 2 different ways you can lose a packet, and you react in 2 different ways. So in the worst case scenario, if there's a packet loss because there was a timeout of your timer, in that case you actually go back to slow start. But in the less drastic case, you might observe a packet loss by a triple duplicate acknowledgement, which we saw that last time. That's when you get 3 acknowledgements of the same number, and that indicates that probably exactly 1 packet was lost. Like, there weren't multiple packets lost, but just 1 packet. That means that you were maybe just slightly above the speed that you should operate at, and so the reaction to that is less drastic. That is to go into fast recovery mode, which is to say basically cut the speed of transmission in half, cut the window size in half, and move back to congestion avoidance. In other words, start growing linearly again. Okay. So usually you do slow start, exponential growth, then you basically stay in congestion avoidance. Fast recovery is basically just the jump down to 1/2, and then you go congestion avoidance is the growth, linear growth. Fast recovery is the jump down to 1/2. This plot here is showing situations where we're only losing packets due to triple duplicate acknowledgements, not due to timer expirations. And the details, which are explained in the book, can be explained in more detail. We're not going to worry about that, but just think about the basic idea and understand the different stages and why they exist and what the differences are. Okay, so if you wanted to implement this, I'm not asking you to implement this. The second project does ask you to implement something like TCP, but we're not implementing congestion control. We're only implementing the retransmissions, and so handling reordering, doing acknowledgements, handling corruptions, stuff like that. Okay. So let's look at this TCP Reno approach to congestion control. I have the diagram reproduced here with slow start at the beginning, and then congestion avoidance has this linear increase and multiplicative decrease. We call it linear increase and multiplicative decrease because it increases linearly. We add a constant every round trip time. But then when we decrease, we decrease by a factor of 2. So that's a multiplicative decrease. So I want you to actually stop and think now about this algorithm. After it gets past slow start, when it's in the steady state, what is the throughput of this algorithm? In terms of, you could look at this example and give me a numeric answer, or we could think about it generically in terms of the maximum rate of the network. Okay, so what do you think is the average throughput of TCP Reno in the steady state? Well, I hope you thought about that. If we look at this abstractly, we can use the variable W to refer to the maximum throughput of the network. We're moving between W and W over 2, the maximum and half the maximum, and we're using this kind of like sawtooth pattern. So we're going up with a certain slope. The exact slope will depend on what the round trip time is and what the maximum packet size is, but it's the same slope every time. And actually, it doesn't matter whether we stretch out that slope or make it sharp, we'll get the same average answer because we're dropping down constantly every time. So this sawtooth pattern averages to the exactly the number that's between the maximum and minimum of the sawtooth, which is 3/4. Okay, so the average is going to be 3/4 of the maximum when we are in this congestion avoidance state using additive increase and this cut in half multiplicative decrease, right? And the way to remember this is to remember how I get my haircuts. Okay, so this is a real story. This is the truth. At least before the pandemic, when I did, go and get a haircut from a professional, I always had a problem in earlier years where I would tell the barber or stylist to cut my hair like not too much, and they would always cut too much. So I tried to come up with a way to tell them exactly how much I wanted to cut. And the best I could come up with would be to say, cut it in half. If you tell them to cut your hair, the length of your hair in half, it's hard for them to like cut too much off because they can kind of like feel what half is and get a good sense of that. So that's what I would always say. I'd say when my hair got too long, when I got to a certain point, I'd go to the barber and I'd say, cut it in half. Of course, that means that if you look at my hair length on a plot of where time is on the x-axis, hair is on the y-axis, when I go to the barber, it cuts down drastically to the 1/2 the level it was before. But at every other time, it's growing linearly, right? Hair grows at a constant rate. One hopes. I hope it keeps to grow. It's growing. And that's what TCP Reno does with window size, okay? The only, the comparison here is that when I notice that my hair is too long and I go to get a haircut, that's equivalent to in TCP when the network experiences too much traffic from the flow, from the connection, and it has to drops a packet off a queue, and the end hosts notice that, and then they decide to cut the traffic in half. Okay, so that's Steve's haircut as an algorithm, as an analogy for TCP Reno congestion control. And of course, you can ask yourself, what's my average hair length? And the answer is, of course, the same as the previous question I asked you, which is 3/4 of whatever length it is at when I tell them to cut it. That's what the average ends up being. Okay. So if you stop and think about this, we've defined rules for TCP where we want the senders to not send too much data, too much traffic, because it might overwhelm the network. And we don't want to do that because it would be inefficient. We don't want the network to be too full because then it'll drop packets. But you might think it's weird that you would purposely slow yourself down when you're using a resource that's shared by so many other people, right? Like, maybe the best thing for you to do if you're sneaky and amoral and you're able to write your own TCP implementation, right? then maybe you should not follow the rules, ignore the rules, and just send data as quickly as possible. Assume everyone else is going to follow the rules, and so other people will be careful about not sending too much data on the network, and the network will not be congested maybe because they're being careful, but you can trample over them and just send as quickly as possible. So is that actually valid reasoning? Are there any problems that would still happen to you if you tried to break the rules? In other words, is there an incentive for you to follow these rules, aside from the fact that it might be difficult for an average person to write their own TCP implementation? I want you to stop and think about that. It's a pretty deep question. Well, I'm not 100% sure, but if you think about it in a very simplistic way, then you can probably convince yourself that it's in your benefit to follow the rules. This won't be true in every case, but in a kind of like general sense, you actually do have an incentive to follow the rules. We know that following the rules benefits others. We know that when others follow the rules, it benefits me. Let's also argue that it benefits myself for me to follow the rules. Okay. So the problem is if you don't throttle yourself, if you don't control your own rate during the congestion, then there's always the possibility, and it could be quite likely possibility, that you're going to have poor performance because you yourself are actually causing the congestion, right? So in particular, if the bottleneck in your connection is on a link that you are the only one using, like if it's the link between yourself, let's say the wireless link between your laptop and your cable modem. If that's the bottleneck and you don't follow TCP congestion control, then you're going to drop a lot of packets there. But it could be anywhere in the network that your traffic is like causing the congestion, and therefore you need to control yourself. Now, whenever the key thing is that you don't really know. You can't observe the network directly. You just observe packet loss. So if there is packet loss, you can't tell whether it's other people's traffic that's causing the congestion or it's just your own traffic causing the congestion. So to be conservative, you can just assume that there's a chance that you're the one causing the packet loss, so therefore you should reduce your rate. Now, maybe if you're really sneaky, you can think, well, maybe I can do an experiment where I don't reduce my packet, I don't reduce my window, my transfer rate, and see whether network still behaves well. But at some point, you'll reach a bottleneck, and at that point, you'll observe packet loss, and you won't know whether it's exclusively due to yourself or to others. That's just my very hand-wavy explanation. I'm not sure how tight this holds, but there's also the fact that there are only a few TCP implementations out there. Generally, TCP implementations come built in with your operating system, so and those ones generally are not maliciously designed because they know the operating system writers are writing code to be used by millions of users who they want to all play well with each other and to give good performance for everyone else. All right, so let's step away from the philosophy of it and the economics of it and look at the performance of TCP Reno with two connections operating at the same time. So I've shown a diagram here, a particular kind of diagram where I have the two connections on two different axes, and the position of a point represents the two numbers representing the two throughputs of the two connections. So in this particular point here that I've shown here in green, we have connection 1 that's operating at a fast throughput because the Y value is high. Connection 2 is operating slowly because the X value of this point is small. Okay, so we have a small X value, a high Y value. So connection 1 is fast, connection 2 is slow. That's how it starts. Okay, these two connections are sharing a link or a path that has limited capacity. Let's say it's a constant capacity. That means that the only valid operating points are inside this triangle I've drawn here. Okay, if you take the maximum throughput is like whatever this Y value is up here where my arrow is, let's say 100's up here and 100 is down here, that means connection 1 can have 100 and connection 2 can have 0, or connection 1 can have 0 and connection 1 can have 100, or they can split it somehow, which is this line in between, right? Or they can use less than 100, which is the whole region of the triangle down here. But ideally, they want to operate somewhere on this line, which is where they're utilizing the maximum throughput of the link. All right. So we're going to start from this point up here and think about how congestion control balances the share of throughput that's given to these two connections. Okay, so it's a pretty interesting exercise, and an important feature of TCP Reno will be illustrated here. Okay. So I want you to think about this. Where does this point move? How does the connection share evolve? Okay. Remember that these two connections are following the TCP rules independently. They're each independently looking for packet loss, and when they see it, they will adjust themselves. They don't even know that there's another connection on the network. They don't know that they're sharing anything. They just know that they have a connection and they're sending data. At some point, they lose packets. They lose packets when the sum of their throughput and their competitor's throughput exceeds the maximum. Okay, but they're only controlling themselves. Initially, one's faster than two, but this is going to change. How does it change? Where does this point move? So please stop and think about that. It might take 2 or 3 minutes to really think through this and figure it out, but it's important. Okay. All right, I hope you thought about that. So as I showed before, the shaded region is where you can operate. This is the uncongested region. Whenever the point moves above the triangle, that means that the sum of connection 1 and connection 2 are using throughput greater than 100. There's going to be a packet loss for one or the other, or both. Okay. When there's a packet loss, then the connections will halve their bandwidth. We'll cut their bandwidth in half. To simplify, let's assume that they both observe packet loss when they're sending too much data. I think that's a fair assumption. Okay. If we're somewhere in this white region up here, and they both have their speed, what it means is that the X position gets cut in half, right? Connection 1 throughput gets reduced by half, and also the Y position gets cut in half. So the Y value is reduced by half. When you do that together, what happens is you are actually moving from whatever point you were on in this white area. You move precisely toward the origin on a straight line toward the origin, 0, 0, halfway to the origin. Okay, so no matter where you are, you move toward the origin halfway into this shaded region. Okay, so the backward arrows in this diagram show that. Like if you're in D, you move toward the origin, you end up here. If you're in B, you move to C. Okay. Now, when you're in the shaded region, how do you move? Well, in congestion avoidance, there you have linear increase. Remember, so both of the connections will every round trip time increase their speed by a constant amount. If you have a point in here where both the X and the Y value are increased by a constant, what that means is that you're moving precisely at a 45-degree angle to the upper right. Okay, because both the X and the Y position increase by the same amount. So you move. So all the upward arrows here are showing that. So they're exactly moving upright at a 45-degree angle. So if wherever you start, what you have is a combination of movements upright at 45 degrees, and then once you cross the line, movements back toward the origin halfway. Okay, so you should be able to convince yourself that by doing that, all you're doing is moving the upward movements are always moving parallel to this line in the middle, right? This equal share bandwidth line. This green line that goes from the origin 45 degrees upward is the line across which every point in this line, connection 1 and connection 2 have an equal share of the bandwidth. That's a good scenario, right? That's what we want to achieve, ideally. Every time we are increasing our bandwidth, like if we're not congested, we're moving parallel to this line. Every time we decrease our bandwidth, because there's a packet loss, we move closer to the line. If we're below, we move toward the origin, and that brings us closer to the line. If we're above, we also move toward the origin, and that brings us downward closer to the line. So whenever we move, we're moving kind of up and down, but we're always moving closer to this equal bandwidth share line in the middle. Okay, so if we're up here, we kind of go like this, and then here, this, and then we get here, and we kind of stay here. If we're down here, we go up and back, and then like shown here, and we eventually get here. So in the end, we should be oscillating back and forth across this line from the origin at 45 degrees, where each of the two connections has an equal share bandwidth. Okay, so this is a really important thing we can observe in TCP Reno, and that theoretically we can prove about TCP Reno under these conditions, where there's fixed bandwidth and so forth, right? So TCP Reno fairly shares bandwidth equally between two participants that are following its rules. This is due to the linear increase and multiplicative decrease that Reno does. Now, you can extend this reasoning to 3 connections, so you can stop and think about what this would look like for 3 connections, what the diagram would look like. But I hope you can convince yourself that it's the same idea, just in 3 dimensions with a kind of plane instead of a line here for full bandwidth utilization. Okay. All right, so that completes the discussion of TCP Reno. Now we're going to move on to talk about some other TCP congestion control algorithms. So the book talks about TCP Reno. This is a good one to have exam questions about and whatnot, because it's an effective design that solves a basic problem in networking, which is to control the rate of transfer, even though you have no observation of what's happening inside the network to avoid congestion. But in practice, there are many more possibilities than just TCP Reno. So Reno was kind of like, I would say, the most successful approach for a long time, but eventually there have been other approaches that have superseded it in practice. On Linux, you can actually change the TCP congestion control algorithm that's being used by using the proc virtual file system. A command like this, for example, would change the TCP congestion control algorithm to use cubic. And if we look at open source operating systems in the past 30 or so years, we can see that by looking at the defaults, so before Linux, the most popular open source Unix operating system was BSD, and BSD actually had a release called Tahoe, and then after that a release called Reno, and that's where the names for the early TCP congestion control algorithms came from. So TCP Reno is called Reno because it was the default built into a BSD release called Reno. So that was in 1990 when Reno was released on BSD. Reno was a minor variation of Reno with a couple of changes, was still used in Linux when Linux rose to popularity in the late 90s and through the early 2000s up until 2004. Linux was using a variation of Reno, but then afterwards it used this binary increase BIC alternative. Cubic is a variation of that up until 2012. PRRR, and then finally BBR, which we'll talk about, which was adopted as a default in 2016 for the latest Linux kernels. And so all these are different ways to kind of control the congestion window size up and down in response to network congestion and to try to set it to the right value. But they operate in slightly different ways. So let's look at some problems with TCP Reno. I mean, the really nice thing about TCP Reno is that it's easy to understand and implement, and that it's very clear that it provides fair share bandwidth between competing users. That's the nicest thing about it. But it seems it has problems on long fat pipes because it assumes that because of its assumption that packet loss is always due to congestion. Okay, so remember, a long fat pipe a long fat pipe is a fast link, like let's say a 10 gigabits per second link that has a high round trip time. So this would be like an ISP's link between, let's say, Chicago and San Francisco might be this example. Okay, it's a really fast fiber optic link, but the round trip time is slow because of the speed of light. Now, if you're following TCP Reno, then you're increasing the window size linearly. That's 1,500 bytes per round trip time. That's a really slow linear increase because the maximum you're trying to reach, 10 gigabits per second, is just really high. Okay, so it actually would take 3.5 hours to move from half of the maximum to the maximum. 3.5 hours. I mean, using slow start, you'll get to the maximum with that exponential increase. You'll get to it really quickly. And so if you're doing a transfer on this kind of a network using TCP Reno, you will basically, unless it's a 3-hour transfer, if it's a short transfer, like only like a 1-minute transfer, then in practice the speed you'll achieve will be 5 gigabits per second, because you'll get to half and then you'll be increasing and increasing, what you think is linearly and consistently, but you're going by such tiny bumps that you'll never even get close to the maximum again. Excuse me. Now that's one problem. But it's an even worse problem related to that is that while we're doing this linear increase, there's a possibility we might actually lose packets not due to congestion, but due to bit corruptions. And there's just such a vast amount of data that we're sending that it's likely there will be a bit corruption that will cause a packet loss. So in 3.5 hours that you're trying to get to the maximum, you're going to send 100 trillion bits in this scenario, right? That's a huge amount of data. And with 100 trillion bits, no matter what technology you're using to encode it and transfer it, you're probably not going to have perfect reliability with 100 trillion bits. So it's very likely you're going to drop at least a few packets. And the problem is, though, that TCP Reno interprets that packet loss to mean that you're going too fast. Well, the problem is you're not going too fast. The problem is just that there's some random corruptions. Okay, and this is actually a homework question, I think. Anyway, so you don't want to... We can solve this problem by growing faster. Both these problems we could solve by growing faster. Instead of growing linearly with a constant that is sensitive, that might be too small for a fast link, we can try to grow exponentially. So the BIC, or binary increase congestion control algorithm, and its later variation cubic, which is cubic binary increase, which is basically the same idea, but slowed down a little bit. The idea there is that you exponentially grow between when there's a packet loss, you reduce your rate. But then from there, instead of linearly increasing, so this blue line is still showing TCP Reno. Instead of linearly increasing, you exponentially increase. You try to do like a binary search, a kind of binary search, to quickly get toward the maximum. Okay, and that should sound good to a computer scientist, right? I mean, unfortunately, by doing that, it seems like maybe you would be giving up some of the fair sharing guarantees that we had before. And when you mix the different algorithms together, like if you mix TCP Reno and binary increase traffic together and cubic traffic together, it's not clear. I don't know offhand whether they would be fair to each other, but I do know that cubic was adopted by Linux for a while to help it deal with long fat pipes. Now, another problem, apart from those long fat pipes, is that, and the problems that exist in both Reno and cubic that I just talked about, the congestion control algorithm that grows exponentially instead of linearly. The problem here is that both of those rely on packet loss to detect congestion, and packet loss means full queues and full queues means wasted time. Okay, let's look at this diagram on the right-hand side to think about what happens when we lose packets, or different states of a network. So with a very simple network model, we have one queue and one link. Okay, as we increase the rate that we're sending, we move from top to bottom here between these states. So at first, we're sending slow enough that the link can handle the rate we're sending, and there's no need to use a queue at all, right? The queue is always empty. Whenever we put something in the queue, it immediately gets sent because the link has plenty of capacity to handle it, right? But once we saturate the link, we're sending data faster than the link can actually handle consistently. Then we have to start queuing things up, right? So the queue starts building, so it's okay at first. We're not dropping packets, but we're building the queue. Okay, this is not a stable scenario. This is not sustainable, right? State 2. This is an intermediary. Eventually, we get to state 3 where the queue is full, and we have to drop packets when they come in, right? The queue is not being emptied at a rate fast enough that we're providing data. So we're going to drop some packets even though we're sending packets consistently at the maximum rate of the link. Okay. So if you think about both Reno and the cubic that I mentioned, regardless of how quickly you're growing or shrinking, if you're relying on packet loss to detect congestion, then that means you're pushing the network to state 3. Okay, it is not only when you get to state 3 where both the link is saturated and the queues are full, only at that point do you slow down, because then you notice there are packet losses, and we said before that packet losses were the only thing we could notice, and that the only thing we could use to control our pace. Okay, well, I'm going to argue that's not totally true here, and so there was some insightful networking research around 2000-ish that came up with an alternative to packet loss to notice congestion. Now, but before we get to that, let's look at this. The problem here is that when we're in this state 3, when we drop a packet, we slow down. Eventually, we slow down to the extent that this queue starts getting emptied, and then we start increasing. We start filling it up again. So if we're using Reno or Cubic or any one of those packet loss-based congestion control algorithms, we're going to be keeping the queues pretty full. And we can call that buffer bloat, is the term you might hear in the networking research community for unnecessary delay in your networking, in your communication, because router buffers are too large and they're too full. So you're increasing your round trip time because you're keeping your queues full. Now, in reality, what you really want to do is, in your congestion control algorithm, the point is to operate at a speed that matches the link speed. So what ideally you'd want to send at exactly the rate that the link can handle. So you'd want to be basically right between state 1 and 2. So you'd want to be sending at a rate, maybe sometimes you'd be sending a little slower than the maximum link rate, but then you'd bump it up so that the queue started to fill up. But then once the queue started to fill up, you would slow down. Okay. And what's the advantage of doing that? So you'd still be achieving the maximum link rate. There's nothing you can do. There's no amount of queuing you can do to make your average speed faster than what the link can handle. Okay. The purpose of the queue is just to smooth it out. Okay. But if we operate with that same maximum link speed but with a shorter queue, we're reducing the latency on the network while also optimizing the throughput. Okay, so Reno and Cubic do a bad job of optimizing round trip time. They kind of create buffer bloat, and instead of keeping queues minimal and keeping delays minimal. So if you're trying to implement a gaming application and using TCP Reno or Cubic, you might end up slowing the interactivity, the delays between the different players affecting each other. Getting their events loaded and shared because they're sending data at a rate that's so fast that the queues are full, right? So I want you to stop and think how you can monitor the network in a different way. Instead of waiting for packet loss, what can we monitor to try to detect that we moved into state 2? What we want to do is send at a rate that keeps us in state 1 until we get into state 2, and then at that point slow down so we get back into state 1, and at that point start to increase. We want to kind of bump between 1 and 2 instead of 2 and 3. How would you do that? Please stop and think about that. See what you can come up with. All right, so the solution is what was invented by researchers in Nevada, and they called it TCP Vegas in honor of their location. And what it does is monitors round trip time of packets to give an idea of what's happening with the queues. And this is different than TCP Reno and Cubic. So instead of waiting for packet loss, what you do is you monitor the traffic and consistently monitor round trip time. When the round trip time starts to get greater, you use that as a hint that queues are starting to fill, which means you're moving from that state 1 to state 2, and you need to slow down. Now, this is harder to make use of because there are other reasons why the round trip time could fluctuate. You need to make sure the application is not introducing variations. But this is in fact usable in practice. So if we think about that process of starting off slow and going faster. So initially we're going slow. If we're below the maximum throughput, our speed might be increasing as we go faster and faster, but throughout that whole process, our round trip time should be very constant, because there's no queuing involved. Every time we send a packet, it goes straight through the queue without waiting, through the links to the destination, same thing on the way back. Of course, I'm assuming a very simple link model, not a lot of competition and consistency in the network, which is not a great assumption, but in this basic model, that's true. Once we get faster, at some point we reach the max throughput of the links. At that point, the queues start to fill up in the routers, and when that happens, then round trip time increases, right? Because now instead of the packets going straight through, the packets are stopping for a little delay at the router to sit in a queue for a little while. Okay, so TCP Vegas monitors that, and when it sees that round trip time is going up in response to the window size going up, in other words, in response to the throughput going up, then it reduces the throughput. Okay, so by doing that, TCP Vegas kind of hovers around the maximum throughput, but it also keeps round trip time optimized near its minimum possible value. So it avoids that buffer bloat and unnecessary increases in the delay of the communication. Now, it turned out that the simplest way to do this that Vegas introduced did not give a fair share of capacity when it was competing with TCP flows using Reno and Cubic. And that's because those other systems, when they would push, if other users are pushing the system toward packet loss, then queues will fill up anyway. And what you're observing is it's harder to observe. You'll end up observing, you'll see increases in your round trip time, but those are caused by other folks, not you so much. And that was a problem. Okay, and I'm not expert enough or well versed enough to know to explain very well why that happened and why and how it was solved, because there was another algorithm similar to this called bottleneck bandwidth and round trip propagation time, or BBR for short, which uses the same idea of monitoring delays, like increases in delays to signal congestion, but it does it in a slightly different way, a more sophisticated way. And by doing that, it was able to compete to experimentally get its, not be starved out by the Reno and Cubic flows. And this system was developed by Google. It was described in a paper in 2016. So at the current time that I'm recording this, it's kind of the state of the art. We've seen that, every few years over the past 15 years or so, and there's been significant innovation in TCP. I think that's sort of slowing down a little bit now, but maybe not. But like I said, I'm not covering these in detail, but just I want to give you the basic idea of what's happening here in the research, and also give you make you aware of it so that you're not surprised when in practice things don't behave exactly like the TCP Reno that you see in the textbook. Okay. Now BBR, just to give you a little bit of an idea, so this green line shows what the TCP window size for BBR might look like in a theoretical case, compared to, again, the blue is Reno and the red is cubic. So it has a different way of, it does still increase its at this time that it's increasing its transmit rate, it's monitoring the round trip times to determine whether it needs to reduce its rate. All right, so I have just a few more slides on TCP. A few more things we should know about TCP to increase its to get maximum performance out of it in different scenarios. Now, one thing that can be a problem with TCP is small packets introducing a lot of overhead. So let's think about an application that writes a bunch of small messages on a TCP stream. Okay, so for example, we have a program that writes OK, ready, go. So these write commands are sending data on a TCP socket. Now, a simple implementation of TCP might send segments, which is to say packets, for every one of these, so 3 packets, which is fine. That would work. But you have to remember that every TCP packet has header overhead. Every packet has overhead. Like there's information at the beginning of the packet that tells the routers. So there we'll see later on that there are the Ethernet and IP protocols that transfer TCP packets have their own headers and overheads, and those are the 40 bytes. That's part of the 40 bytes of overhead that is included, but TCP itself also has some overhead. So every TCP packet has 40 bytes of header overhead, including those 3 protocols, Ethernet, IP, and TCP. So even if we're sending just 3 bytes of data, then we are also sending 40 bytes of header along with it. So this message here, OK, ready, go, has 3 bytes, 6 bytes, and 3 bytes for the text, for the message itself, but then each one of those has an additional 40 bytes of header overhead added. So the total is 132. If we could somehow merge those together, that would reduce network load. And because TCP communication is stream-based, like in TCP, these are not actually separate things. These are just bytes in a stream. So, it's a pipe abstraction where there's no separation unless we want to create it in an application. Like HTTP has to explicitly put new lines and content lengths to tell the application when the messages stop. Otherwise, on the TCP stream, the data is just continuous. So to do this merging to save space and to send less data on the network, we use Nagle's algorithm, or Nagle's algorithm is a description of how to do this. And it's pretty simple. It just means that if you get a segment, especially if it's small, your implementation of TCP can wait before sending. And the specific rule for Nagle's algorithm is to wait before sending unless there are no unacknowledged segments outstanding. Meaning if it's the very first segment, then go ahead and send it. But if it's not the first one, then wait and accumulate them. Okay. Eventually you get to a maximum size of a packet, in which case you have to send. That's fine. That reduces the overhead of data that you send on the network, so it makes your applications more efficient in terms of the bits that you're sending. You send fewer bits. But, there's some clear downsides to that you probably are already thinking about. Like, you're slowing down your application, you're introducing latency in your applications, and some applications, especially interactive applications, will really not like that. So sometimes you really want to send those small messages as quickly as possible, because those small messages might be time-sensitive data, like GUI events. Like if you're using if you're clicking on things in a game or some application that's remote that's hosted over a network, you want to get responses to those clicks immediately. Even if the message that I clicked is very small, it's important that I send it as soon as possible if something important is going to come back in response to that click. So there's no one way to design a TCP socket that works well for both bulk transfer apps like file transfer apps and interactive apps, because they have different needs. A file transfer app, your goal might be to make it efficient, for an interactive application, your goal might be to reduce the latency of the performance more so than the efficiency. So there are socket options for TCP that kind of give the application a little bit of control of the underlying TCP. And this breaks the idea of abstraction. So previously we thought of TCP socket as this abstract thing that just somehow provided a stream that somehow, broke things into packets and made it work. These socket options give a little bit of control, a little bit of visibility and control over what's happening underneath in TCP to the application. So, for example, TCP no delay disables Nagle's algorithm. So every time you write, your data is sent immediately. This is good for those interactive user interface applications. The reverse of that is no push, which is even more aggressive than standard Nagle. So even that first packet that you send will wait until you get a full packet of data before sending. So this is good for a file transfer application. And finally, there's a push bit which you can set on data that you send in TCP to indicate to the other side that the application should receive the latest data at that time instead of queuing it up and sending it in one big chunk. But it's not a very important thing, but you might see a PSH in a Wireshark trace or something. That just means the application, usually that's at the end of a write call that the application made. Another little detail of TCP are Keepalive messages. So we'll see why this is important when we later on talk about IP and NATs, which I'm not going to try to explain now. But just notice that when you can have a TCP connection open for a long time that's idle. So you have two machines that are like ready to talk to each other. They have each other's sequence numbers. They know that they've acknowledged everything that was transferred so far. They're ready to send new data. They know what next sequence number to expect, what next acknowledgement to send, but they're not sending anything at the moment. Because of there are these middle boxes, for example, NAT routers that block traffic that is unexpected. But they allow outbound connections to be made. So for those to not start blocking your connections, your packets, you might need to send at least like one packet per minute between the two machines, even if there's no data to send, to make sure that the router in between keeps the port mappings open, basically. To be honest, this slide might make a lot more sense if I just moved it to the lecture on NAT, and maybe I'll do that and repeat it. But basically, what you can do in TCP is send a Keepalive message, which is a message that has a sequence number that's smaller than what you expect. So basically, you purposely send old data, and that triggers an acknowledgement back telling you what, like if I send a sequence number of 9, even though I've already sent 10, the receiver will send me acknowledgement 10. That's just a way for the TCP implementation to force a packet to come back. And by sending a packet back and forth, you are reminding the firewalls in between, basically, that these two machines are still communicating and that they should be allowed to communicate in the future, basically. There are also some applications that have their own Keepalive messages at the application level, but we're talking about TCP level stuff. This is when the application is doing absolutely nothing, but TCP is sending Keepalive messages. All right, so that's all I have for today. To recap, mainly I talked about congestion control, which is a way to control the rate that you're sending data so that you don't overwhelm the network. TCP has dynamic congestion control, a dynamic congestion window, and it's controlled by heuristics because it's really impossible for the host to know all the complexities of, all the complex things that are happening in the middle of the network that might affect, that might influence the maximum rate at which you can send at a given time. And every connection is different, and you have to kind of like probe to figure out what the correct rate to send data is. If you send too fast, it's inefficient. You'll drop packets, cause more congestion for everyone. Reno is an algorithm that is simple but effective for congestion control in TCP. And it has 3 phases. Slow start involves exponential growth to let you quickly find what is approximately the maximum network capacity. And at that point, you switch to the next stage, congestion avoidance. That's where you want to try to spend most of your time, which is where you're sending at basically the same rate, but you linearly grow increase the speed. So like one packet size per round trip time, until eventually you lose a packet again, in which case you cut the window size in half. That's fast recovery. This TCP Reno style of congestion control is what's known as it's an additive increase, multiplicative decrease protocol. That's important. And sometimes you'll see that with an acronym, AIMD. And the benefit here is that you can very easily theoretically show that this provides fair sharing of the bandwidth between the competing users. I had that little diagram to show that, where you approach the origin, that 45-degree fair share line in the middle. I also talked a little bit about newer congestion control algorithms that solve some of the problems with Reno on long fat pipes. There's also an article on this. If you're interested, download the PDF here and click the link or Google, BBR congestion control, see what you come up with. And basically, the way these work, well, these are different. So cubic increases faster than linearly by kind of binary searching exponentially up to the maximum. BBR is an approach that minimizes the delay on the connection as well as optimizing the send rate to achieve the maximum throughput. So this avoids filling up queues unnecessarily, which is pretty cool. But it's a lot more complex than Reno. I also mentioned at the very end that TCP behavior can be controlled with socket options. So this allows the application to kind of dig under the hood or under the covers, depending which analogy you want to use, to tweak TCP, which normally TCP operates kind of automatically and magically for applications, but there's a slight difference in the requirements of interactive applications versus bulk transfer applications and everything in between. So we have Nagle's algorithm is a way to reduce the overhead of TCP by merging small packets. On the other hand, we have there are ways to disable that using socket options. I also mentioned TCP Keepalive messages as a way to keep middle boxes aware of a connection by periodically sending kind of nonsense messages back and forth. But that'll make more sense later when we talk about NATs. All right, hope that made sense for you. See you later.